Hello everyone, I'm Yiwen Zhang from the University of Michigan. I'm here to present our work, Justitia, which is a system designed to provide multi-tenancy support for hardware-based kernel-bypass network. Let's start with why people use kernel-bypass networks. We know that in traditional networking, the operating system is responsible for handling data transfer. Kernel-bypass networking, on the other hand, removes the kernel from data path to provide lower latency and higher throughput. Among those emerging KBN technologies, hardware-based KBN, such as RDMA, offloads data transfer tasks to specialized network interface card. Such offloading further improves performance as well as CPU efficiency, making hardware-based KBN a popular choice in large-scale cloud deployments. However, being deployed in cloud environment leads us to another question. Since cloud data centers are inherently multi-tenant, we are wondering what happens when multiple applications coexist and share the same NIC. In particular, we're interested in three types of applications. First is bandwidth-sensitive applications, which send large messages and desire high bandwidth. Distributed storage is one of the examples. Second, we have throughput-sensitive applications, which send small messages in batches and target for high message rate. And lastly, we have latency-sensitive application, which send sparse small messages with low latency requirement. Applications such as key value store and resource disaggregation, depending on their use case, fall into the last two categories. Now, when those applications coexist and compete with each other, we have this concern about multi-tenancy because in hardware-based KBN, when all the work is offloaded to the hardware, the operating system has no control but to rely on the NIC to isolate among different applications. In fact, the multi-resource nature of the NIC further complicates this problem. We find that there exist two primary resources that needs to be shared on the NIC. Link bandwidth is one of them, and is mostly consumed by bandwidth-sensitive applications to issue large DMA requests. The other resource is execution unit throughput, which determines how quickly your NIC can process small messages. Throughput-sensitive applications consume this resource to send small messages in batches. As you can see, when these two types of applications coexist and compete, there could be potential resource contention on the NIC. Latency-sensitive applications, on the other hand, does not saturate either of the two resources, but can potentially be blocked by large messages due to head-of-line blocking. Therefore, we start with this simple question. How well does hardware KBN provide performance isolation? To answer this question, we perform a series of experiments. Each time, we let two types of the application compete, and we observe whether their performance is affected compared to the case where they're running alone. In the experiment, we use a simple single sender, single receiver setting to exclude the noise from network congestion. After trying all the combinations across major RDMA implementations, we conclude that performance isolation is not guaranteed when bandwidth-sensitive applications are present. In the next slides, I will highlight how latency and throughput-sensitive applications lack protection under the setting of InfiniBand. First, let's see the case where a latency-sensitive application sending 16 bytes of messages compete with a bandwidth-sensitive application sending 1 megabyte messages. In the figure, the vertical axis is the 99th percentile latency of the latency-sensitive application, whereas the horizontal axis represents the aggregate bandwidth of the bandwidth-sensitive application. The blue dashed line shows the original performance when the latency-sensitive application is running alone. When a bandwidth-sensitive application joins, as you can see, its tail latency performance becomes worse by 2x. Moreover, if we add more bandwidth-sensitive applications, the situation will become much worse very quickly. The bandwidth performance, on the other hand, doesn't change as much. So this clearly indicates that latency-sensitive applications need isolation from bandwidth-sensitive applications. Now we move on to throughput-sensitive applications sending 16-byte messages in a batch of size 64, competing with the same bandwidth-sensitive applications as before. The vertical axis now represents the message rate of the throughput-sensitive application. As we can see, when we have these two applications compete, the throughput performance in terms of message rate will drop to less than 1/3 of its original performance. And like before, when we increase the number of bandwidth-sensitive applications, the throughput will drop by even more. We also observe the same issue exists in a lot of real argument-based applications, including DARE and FAST. Their latency or throughput performance can get significantly affected if they are not in good isolation. At this point, we see that although native hardware-based KBN can provide good performance, when applications are running alone, they do lack multi-tenancy support. This motivates us to design Justitia, which is a system to provide multi-tenancy support for hardware-based KBN. We want to achieve this in an efficient, scalable, and transparent way without modifying applications, operating systems, or hardware. Now, before we talk about the actual design, let us first consider the root cause of this problem. It's actually due to the fact that the tenants can offload any amount of work to the NIC at essentially no cost. For example, the tenant can consume a lot of NIC resources by either specifying arbitrarily large messages or by opening a lot of connections for their data transfer. Therefore, the idea here is to insert a software layer between the tenants and the NIC. So instead of letting the tenants directly submit their own messages to the NIC, we issue these operations for them. With the help of this extra layer, we can control what goes into the NIC and when these operations will arrive at the black box hardware. This will effectively prevent tenants from hogging NIC resources. To incorporate this idea, we implement Justitia with two components, a Justitia daemon and a Justitia shaper. In a high level, the daemon performs latency monitoring and proactive rate management, whereas the shaper enforces resource utilization provided by the daemon. Before we dive into the details, let us go through an overview to see how Justitia handles different types of applications. For latency-sensitive applications, they bypass Justitia and directly interact with the NIC in order to preserve their low latency performance. Bandwidth-sensitive applications, they first enter Justitia shaper, where their messages are split into smaller sub-messages to mitigate head-of-line blocking. At the same time, the Justitia daemon is performing latency monitoring. Based on the current latency profile, it calculates a safe utilization rate to maximize the NIC resource utilization without violating the latency target. Based on this calculated rate, it then generates tokens for the shaper to fetch, and the shaper uses this token to issue operations to the NIC. Justitia handles throughput-sensitive applications in a way very similar to the bandwidth-sensitive applications, except that the message from the throughput-sensitive applications will not be split inside the shaper because they are small. Next, I'm going to highlight several design choices we make in Justitia. One of such design choices we have in the daemon is passive latency monitoring. Probing every message in all latency-sensitive applications can cause overhead in both latency performance as well as CPU usage. Instead, we maintain a reference flow and measure its latency for the latency monitoring. The idea behind this is that if the latency of the reference flow gets affected, then the other latency-sensitive applications are also getting affected. Plus, adding this extra flow does not hurt the original latency performance, as we find that multiple latency-sensitive applications can coexist well with each other. Another design we want to highlight is the multi-resource token generated by the daemon. As we mentioned during the overview, both bandwidth and throughput-sensitive applications need to grab this token to be able to send the message to the NIC. Instead of generating two types of token for these applications, we use the same token to represent either of the two NIC resources based on the application type. Each token can represent one split chunk of bytes for bandwidth-sensitive application, or an equivalent number of messages in a batch for throughput-sensitive applications. And the conversion of the two values can be determined by the maximum capacity of the NIC in terms of link bandwidth versus execution throughput. Another challenge we have in the shaper is to transparently split messages such that we don't need to have the tenants to modify their own code to be able to use Justitia. Here we label things using RDMA terminology, but think of QP or Q pair as a pair of queues which can store send and receive requests, and CQ here means completion queue, which is used to store completion of your requests. So the idea here is to have Justitia's own Q pair do most of the work, but still have the NIC generates a completion back to the user when the entire message is done transferring. Let us go through a quick example. Say we have a bandwidth-sensitive application trying to issue a large message. This message will first go through Justitia shaper, where it gets split into multiple chunks of smaller data. And then the split queue pair will do most of the work. This includes having the NIC fetch the request from our own queue pair and write its completion into our own completion queue. And we'll repeat this process for almost all the chunks except for the very last one. For the very last chunk, we'll instead use the user's own queue pair to submit this request. In this way, the NIC will be able to write its completion back to the user's completion queue so that the user can fetch for its completion notification. And this will also mark the completion of the entire message. In the interest of time, we couldn't cover all the details in the paper. So if you're interested, please refer to our paper for more details. Finally, we want to highlight some evaluation results from our paper. We'll show that Justitia can provide isolation while maximize utilization. It can work well for real RDMA-based applications, and it can complement congestion control in in-cast scenarios. First, we applied Justitia to one of the cases we see early, where one latency-sensitive application is competing with 4 bandwidth-sensitive applications. With the latency target set to 10 microseconds, we observed that Justitia can provide good isolation to latency-sensitive applications, and at the same time achieve good utilization for bandwidth-sensitive applications. And we can do this in both InfiniBand and Rocky. Next, we show that Justitia can also work with real applications. Here we have a latency-sensitive application called DARE, which is performing state machine replication, competing with a bandwidth-sensitive application called Quail, which is a distributed storage. As we observe, Justitia is able to preserve DARE's performance without sacrificing too much of Quail's bandwidth resource. Lastly, Justitia can also complement existing congestion control, such as DCQCN. In this experiment, we have a setting of 33 senders, and 32 of the senders are running bandwidth-sensitive applications to a single receiver, whereas the very last sender runs a latency-sensitive application. We can observe that Justitia further improves its tail latency performance by complementing DCQCN. We handle incast by implementing receiver-side updates inside the shaper, and the basic idea is to have the receiver inform the senders the existence of other senders so that they can correctly update their safe utilization rate. More details on how we handle incast scenarios can be found in our paper. With this, I'm going to conclude my talk. Today, we introduced Justitia, which is a system to provide multi-tenancy support for hardware-based KBN. Justitia code is open source, and it's available on our GitHub repo. So thank you for listening, and I'm happy to take questions.